Imagine you are the CEO of a ride sharing company like Uber or Lyft. Your primary goal is simple: maximize your revenue while ensuring riders quickly find cars. Today, I'm proud to present on behalf of my team a machine learning project titled Revalance. Revalance is a dual agent reinforcement learning platform designed to optimize ride sharing matching efficiency. Here is a quick look at our agenda. I will start by breaking down the core problem of matching efficiency. Next, I'll define our dataset and explain why our team specifically chose reinforcement learning. Then, I will dive into our system architecture, explore the inner workings of our two AI brains, the pricing agent and the dispatch agent, and discuss our implementation. Finally, I'll share our evaluation results, critical engineering challenges, and outline our individual team contributions. Let's dive right into the core issue. Ride-sharing platforms constantly battle a matching efficiency problem. Relying on static pricing fails to capture real-time demand spikes, which ultimately results in lost revenue. On the flip side, you have uncoordinated drivers aimlessly circling in low-demand areas, which wastes fuel and increases passenger wait times. To solve this, our team built the Revalance system. Our core value proposition is a dual agent AI system. One agent simultaneously optimizes revenue via dynamic pricing, while the other minimizes wait times via proactive driver rebalancing. Furthermore, to strictly adhere to our assignment constraints, we achieve this using exactly two reinforcement learning models and absolutely no deep learning models. To train our models, we needed real-world data that is published on the internet. We utilized the New York City Yellow Taxi trip data from January 2023, sourced publicly from Kaggle and the TLC. We processed over 500,000 historical trip records. We then built a central simulation engine that replaced this historical dataset to simulate a live day. It continuously calculates the current supply of available cars and the demand of hailing passengers for every single zone. You might ask, why not just use supervised learning? While supervised learning predicts demand, reinforcement learning actually finds the optimal action or price that maximizes long-term revenue. It accounts for how a price change right now affects future demand elasticity. For dispatching, a simple greedy algorithm just sends a car to the nearest passenger. Our RL agent learns to send cars to where passengers will be in 10 minutes, maximizing utilization over time. Our system architecture takes a microservices approach centered around a central simulation engine. Component A, our pricing service, queries our first RL model to set the optimal price multiplier for a zone. Component B, the dispatch service, queries the second RL model to direct idle drivers to anticipate demand. All of this data is pushed to a frontend that visualizes the city map, real-time price surges, and car movements. For model A, which was my primary focus, I developed the pricing brain. I used an algorithm called fitted queue iteration or FQI powered by random forest regressors. For model A, which was my primary focus, I developed the pricing agent. I used an algorithm called fitted queue iteration or FQI powered by random forest regressors. FQI is a stable batch RL method, meaning it learns effectively from our static NYC taxi dataset without needing a live simulator during the offline training phase. To handle real-time dynamic pricing, I wrapped this FQI model inside a Monte Carlo tree search, or MCTs, framework to look ahead and evaluate future states. The state space for my pricing model factors in the time of day, location ID, current demand level, and competitive price index. The actions the agent can take are discrete price multipliers. The reward function is the price multiplied by the number of rides accepted. However, I applied a penalty if setting the price too high causes the conversation rate. The state space for my pricing model factors in the time of day, location ID, current demand level, and competitor price index. The actions the agent can take are discrete price multipliers. The reward function is the price multiplied by the number of rides accepted. However, I applied a penalty if setting the price too high causes the conversion rate to drop below our threshold. For Model B, my teammate developed the dispatch agent. They implemented SARSA with Lambda, utilizing linear function approximation. Because dispatching is a sequential navigation problem, it is better suited for an online RL method. A critical feature here is the use of eligibility traces, denoted by lambda, which allows the model to credit a pickup happening now back to a move action made 10 minutes ago. To handle continuous coordinates without deep learning, my teammate utilized tile coding. The state space for the dispatch agent observes the driver location, neighbors on demand, and traffic congestion index. The actions are directional movements: stay, move north, south, east, or west. The agent receives a massive positive reward of plus 100 for a passenger pickup. Conversely, it receives a minus 1 penalty for every minute driver empty, and a minus 10 penalty for a stuck out, which means being in a zone with zero passengers. Bringing this to life required a robust engineering pipeline. On the back end, our system architect used FastAPI as the simulation conductor to run the clock and update states. They also set up a PostgreSQL database to log simulation results. For the front end, our developer built a React dashboard. We connected the two using WebSockets for real-time state broadcasting. Everything is fully containerized using Docker Compose, so it runs flawlessly on any machine. I am thrilled to report our results were highly successful. After heavily optimizing the reward functions, my FQI pricing agent achieved an R squared score of 0.9088, explaining 91% of the Q-value variance. The mean square error dropped to 8.02. Most importantly, it achieved a 62.2% win rate against baseline static pricing. Economically, the model brilliantly learned that NYC taxi demand is largely inelastic, often choosing to discount rides at 0.8 times in oversupplied zones to capture more trips. The dispatch agent also performed exceptionally well. In evaluation, the SARSA agent achieved an average reward of 227.64. This outperformed a random dispatch baseline by 10%, and it vastly outperformed a static stay-in-place agent by 120.6%. By mapping out the grid with tile coding, the agent effectively learned to navigate toward historically high demand zones like Times Square, Greenwich, and Penn Station. Building this wasn't without hurdles. Our biggest challenge was latency. Standard Monte Carlo tree search requires thousands of rollouts, which would freeze our web simulation dashboard. I solved this by using truncated rollouts, limiting the tree depth, and querying the FQI random forest to estimate remaining value. Additionally, to ensure our simulation's transition accuracy was realistic, we calculated actual price elasticity coefficients from the dataset and used Poisson distributions to model stochastic real-world demand drops. As part of our critical analysis, we identified room for future improvement. Currently, our dispatch agent is limited to simple directional movements like moving north or south. A future iteration could expand this action space to be of enough complexity. Additionally, while our two models are successfully split into separate components, they do not directly communicate with each other. Implementing multi-agent communication could improve overall fleet synchronization in future builds. Here is a summary of our team effort. In conclusion, Revalance proves that reinforcement learning is a highly capable tool for solving complex meshing efficiency problems. By relying on foundational algorithms like FQI and SARSA, we created a highly effective platform without ever relying on deep learning architectures, strictly following our assignment constraints. We successfully built an intelligent system to optimize fleet revenue and minimize wait times. Our models were trained using the publicly available New York City Yellow Taxi trip data from January 2023. The assignment requirements and rubric guided our algorithm selection and presentation formatting. Thank you for your time and attention.
Imagine you are running Uber or Lyft. Every single minute you are fighting two battles at once. What price you charge? Too high. Riders leave. Too low. You lose money. Where are your cars? A driver sitting idle in the wrong neighborhood means missed fares and frustrated customers. Now imagine handling both of those battles to two AI agents trained on 500,000 real New York City taxi trips, making decisions in real time. That's Revalance. Before we talk about the solution, let's understand why this is hard. A city isn't static. Demand shifts by the hour, and the neighborhood by the weather. A pricing decision you make at 8 a.m. looks completely different by 9 a.m. And the car you position in downtown Manhattan might be exactly wrong if the crowd is heading to Brooklyn. Traditional systems handle this with fixed rules, such as peak hours, reposition based on the yesterday's data. It works, but it leaves enormous value on the table. Revalance takes a different approach entirely. It learns. The moment you hit smart simulation, the platform comes alive. You control a fleet of 100 vehicles. You can push the speed up to 5 times. And across 96 simulation steps, two AI agents are silently making hundreds of decisions every step, every zone. At the top of the dashboard, the scoreboard updates in real time. In one computer run, the numbers look like this: $21,668 in total revenue, 4,976 rides completed, 6,284 total demand, 1,308 unserved. What gives a service rate of 79.2 at the average price of 1.12 times? That 79.2 isn't a failure. It is the system being honest. Not every ride can be served, but the ones that are saved profitably and efficiently. Below the scoreboard sits the heart of the dashboard, a live 20-zone grid, each zone showing three numbers: demand, supply, and rides completed. And each zone has pricing badge. Some show zero point 0.8 times in green, a discount because supply is outpacing demand. Others show 1.2 times in teal or 1.5 times and 2.2 times in the real surge in price. Because riders are completing secure cars, looks at zone 231 and zone 233, both sitting at 2.0 times surge. Zone 79 and Zone 230 is 1.5 times. Meanwhile, Zone 161 with 6 cars and 6 demand perfectly balanced, calmly and calmly at zero point 0.8 times. A human making these calls. Model A is watching every zone, every step and flipping those pages automatically. How does it decide? Model A uses technique called fitted queue iteration. Instead of memorizing a rule for every possible situation, it trains a random forest of 200 decision trees to estimate the best pricing action for any market state. It asks one question repeatedly. If I, if I charge this price right now, what do I learn? What do I earn today? And what does it set me up to the earn tomorrow? The training results are visible directly in AI module steps. Ask guard of zero point 0.9 MAE of 3.57, win rate of 62.2, and average Q value of 106, meaning the agent consistently expects strong long-term reward from its decisions. The action distribution chart, chart tells the strategy plainly. The agent defaults to zero point 0.8 times and 1.2 times most frequently. It isn't aggressive by default. It surges with when the data justifies it, and the discounts when supply is heavy. That intelligent resistant. And with the interactive prediction panel, you can test it yourself. A zone and hour, demand level, supply count, and day. It predicts optimal price, and agent tells you exactly what it would charge and why.
But perfect pricing means nothing if there is no car to send. That's where Model B take over. The fleet dispatch agent running SARA, its job is to look at every idle vehicle and decide stay here or move north, south, east, or west. The dashboard shows its action distribution clearly. 38.3% of the time it says stay, 10.2% move north, 7.9% move south. The agent is not randomly shuffling cars. It's make deliberate conservative repositioning calls, moving only when the data say a better opportunity is nearby. And the key to why its work is eligibility traces. The lambda in SARA, when a car moved two zone over and pick up a highly paying passenger 10 minutes later, that delay reward travel backward through the agent's memory, reinforcing every routine decision that led to that movement. The performance numbers are stark. AI rewards 227.6, random baseline 286.93, but that's introverted mean the AI is outperforming random by 10% and outperforming static crowding by an extraordinary 120.6%. That's not an incremental improvement, that's a completely different class of decision making. This is where relevant does not just something most RL platforms never bother to do. It make agents explainable. In the AI modeling tab, you can switch between model A and model B and integrate them directly. For model A, the how fitted queue iteration work section break down every component fitted iteration, the Bellham equation, random forest approximation, and supply demand pricing logic in the planning language alongside the math. You are not just watching the agent decide, you are watching how it decide. This is what separates Revalance from the black box. The algorithm are open, the key values are visible, the reasoning are readable, and that the movement reinforced learning stop being research concept and become something you can actually trust in prediction. So Revalance brings the three disciplines together in one platform: advanced reinforced learning, real world operation research, and whole stack engineering built for live observability. The dashboard show you the revenue, the zone grid show the decision, the AI modeling tab show the reason behind them. Most reinforced learning system live in research paper. Relevance lives in the street where 100 cars are moving, 20 zones are shifting, and every wrong decision costly costs real money. That's why make it genuinely impressive. Not just that it work, but that you can watch it and think.